Hey guys, we're going to do a little bit of kinematics problems here just kind of as a practice. Hope that this kind of makes sense and pulls some of those ideas together. Before we get started here, I want to remind you that there's only 5 variables that we keep up with, and there's only 3 formulas. So it is imperative that you keep those in mind. We are trying to measure and record the displacement, the distance that I've traveled from beginning to end. That should be measured in meters. I need the initial velocity in meters per second. The final velocity should also be in meters per second. The acceleration gets measured in meters per second squared. And for time, t, we always measure in seconds. If it says minutes or hours or something else, you want to change it to seconds. Okay, see how all these have seconds in them? It just makes it work. We always work in meters, always in seconds. If you see something else, I would change it. Sometimes you can slide on it, but those are always safe. Now, those are the 5 variables, but I've also got 3 formulas that tie those 5 together. They look like this. V equals V naught plus AT, X equals V naught T plus 1/2 AT squared. If you don't have these down somewhere on a piece of paper, then please hit pause. Go ahead and hit, and get a piece of paper and write those down. You need those 3 formulas and these 5 variables, and that should do pretty much everything that we're going to do here in one way or another. So let's get started with that. See, I already told you a lie. Adding vectors is in there in that first chunk of stuff. So here's a vector addition problem. I guess we've also got the right triangle trig problem. So that might be one more thing that you could put in there, but that's math stuff, right? This is a math problem, really. Whenever we're trying to add vectors, what we need to do, and I've got a whole video on vectors. There it comes. Okay, there are 4 steps that we want to do here. Step 1 is always to get the x component of the resultant. Now remember that I've got 3 vectors, this one, and this one. And you could draw a little picture here. If I go 32 steps at 143 degrees, I'm always starting right here at 0, rotating counterclockwise. 143 might be about there, and I need to go 32 steps that way. Okay. Next up, I want to go 127 steps at a 20-degree angle. So once again, draw a little line pointing off to the right. That would be your 0 degree, and rotate counterclockwise. 20 degrees might be up something like that. This time we're going much farther, 127 steps, whereas this one was 32. And then finally here we want to go 75 steps at a 14-degree angle. Here's my 0. 14 to be, say something like that. And it's not quite as far as the other one, but longer than the first one, so maybe there. Okay, went 75 steps. You got a 14-degree angle. Would look like that, and you can see pretty easily what this resultant does. It starts down here, it ends up at the top up there. That would be the path. The result is that we moved from here up to there, so we call that R, the resultant. And I've got vectors A, B, and C, and when I add them I get the resultant. Got it? Okay, we need to know how to do that with math. The first step would be to get the x component of R. I'm just going to come in here and draw a little green line up underneath. See how R right there, that red line, takes me to the right and up? For step 1, you want to know how far to the right it takes you. So I'm really looking for this right here. That would be R sub x. And we want to do that, so I'm going to just take the numbers here. You always use cosine for step 1. So I need to go 32 cosine 143 plus 127 cosine 20 plus 75 cosine 14. And what that does is it's going to give me the x component of A. See how that goes a little bit to the left? X component of B would be a little bit to the right, pretty good bit to the right actually. And the x component of C, this horizontal distance right there, when I go a little bit left and a good bit right and some more right, I end up going this distance right there. So we're looking for that number. You get your calculator here, which evidently I didn't pull up, so I got to go find my calculator now. thought I had it up. And when you start pushing buttons, you make it look just like it says. Remember, you got to check the mode. Make sure that it's set to degrees. If not, use your arrow keys and go down, down, over, and hit enter and all that. But once you've got it in the right thing, then you can go 32 cosine 143, and you do have to close off that parenthesis right there. Plus 127 cosine 20, close it. Plus 75 cosine 14. It's going to take care of all the positive, negatives, lefts, right, all that stuff. And it's going to tell us that we ended up 167 steps to the right of our starting point. So I'm going to put that number right here. Notice that's a positive number, and yep, we ended up to the right, which would be a positive number. So that looks good. Next up, we got to do the same thing, but do it in the Y direction. So I'm going to try to find a different color here. How about some hot pink? And step 2 would be to get the R sub Y, the Y component of R. You're going to do exactly the same thing here, except this time you're going to do it with cosine. So I'm going to just make a little mark here. Take all those cosines, swap them out to sines, and you'll notice that A takes us that high up, and that B takes us up some more here, and then C takes us up some more. So if I take that up and up and up, if I add those 3 ups, what I end up with is this height over here. That would be R sub Y, the Y component of the resultant. And I'm going to just flip over here to the calculator and get this. The cheat, the quick and dirty way to do this is to hit second enter. It pulls that back up. And instead of cosine, I want to put sines right there. Make sure you get all 3 of them. And then hit enter. Okay, 80.8 is good enough. 80.84 if you're fussy about such things, but somewhere in there. All right, and then what we've got now is a triangle that goes 167 this way and 80.4 this way, and we'd like to know the length of this. Well, I can do that with the Pythagorean theorem. I've got 2 sides of a right triangle, and the third one would be given by the Pythagorean theorem. So I need to take this number and that number and run it through the Pythagorean theorem. All right. And that would be the square root of 167 squared plus 80.4 squared, and 185, somewhere in there. All right, and that would be the length of this line right there. We are now 185 steps away from there. Notice that we went 32 and 127 and 75, so that's about 230 steps we took, but we were changing direction. We went left and then we went right. Some of that canceled out, up, up, up. The end result is that we ended up 185 steps away from where we started. I'd also like to know that angle, and the angle we're interested in would be this right here. And so notice that I know the opposite, and I know the adjacent. Opposite and adjacent make me think of tangent. I want the angle, so I've got to do the arctangent here, and theta equals the arctangent of the opposite 80.4 over the adjacent 167, and second tan 80.4 divided by 167 would be a 25.7 degree angle there if I did that right. All right, I'm really interested in these 2 numbers right there. And at this point, I could come along and say the vector R is 185 steps away from home, and you'd have to go at a 25.7 degree angle to get there. All right, so that's what they want you to do. All the vector problems work out exactly like that, and you're trying to get that answer right there. Okay. Now, some of them, let's say this is the y-axis and the x-axis here. I could have ended up over here somewhere. And you know, when I did the arctangent, it might have said, well, this is the angle that you're finding right there. You know, if it was 80.4 down, negative, and 167 to the left, negative, if this answer had come up negative and this one negative, that would be go left and go down. All right, so we'd be talking about this resultant then. I don't want that angle right there. You know, when I get 25.7, I don't want to measure from here. I want to measure all the way around from here. So I'd have to go this 180 degrees, and then I'd have to go 25.7. So about 3/4 of the time we got to fix this thing, and 180 plus 25.7 would be the fixed angle there. We don't have to fix this one because we're in the first quadrant. If you go right and up, you're okay and don't have to do anything. But anywhere else, you got to fix it. This quadrant would be 180 minus whatever arctangent gives you. This one's 180 plus, and this one is 360 minus, and then this is whatever arctangent comes up. Okay, there's a video on that. Go check that, or give me a call if you want to work some more of those. This is actually a trig problem right here. I got a radio tower. They give me the height of it, so I'm going to draw a little radio tower here, whatever, and then the ground goes that way. There is a cable that goes from the top down to the ground and makes a 26-degree angle. I know the height of this thing, 47 meters. We'd like to know the length of that cable. So we recognize that this is a nice right triangle. I got a right angle right here, and so I get busy and name the parts. This would be the angle theta. Straight across from theta is the opposite, and I'm looking for the hypotenuse. And I'm thinking about my trig functions, trying to find something that involves opposite and hypotenuse, and of course you end up with tan theta equals opposite over hypotenuse. Okay? Now, as it turns out, I know the opposite, and I know theta, and I would like to find the hypotenuse. So I need to do something here to get the hypotenuse by itself, and the thing that I need to do is to solve it with algebra. And if I come through here and multiply this side by the hypotenuse, then that would cancel on the right, but I'd have to do it over here as well. Okay, so now I've gotten to that point. I've got the hypotenuse out of the basement. Get it out of the basement first. Next up, I can come through here and divide both sides by tan theta, because I want hypotenuse by itself. So I got to get rid of that tangent theta. And when I do that over here, then I'm going to end up with the hypotenuse is equal to the opposite divided by the tangent of theta. Okay, I got all those numbers, so we're doing good. This would be the length of the cable. I'm going to just call it C here for cable. The opposite was 47 meters, and then I divide by the tangent of 26 degrees, and 47 divided by tangent 26 works out to 96 meters. I need to go to the hardware store and buy 96 meters, a little bit more there. But you know, you could deal with that later. 96 meters, 0.3 or whatever it was. You know, maybe you got to buy 2 meters to tie off up here and another 6 meters to tie off down here or something. You know, so you'd work all that in. In real life, you would have some sag here that would be inevitable unless you could pull that thing really, really tight, at which point you're going to pull your tower over. So, you know, you'd have to add up for that too. But that's all they want you to do here. Don't worry about the sag. Don't worry about the extra on the ends. But that straight line distance from the ground up to the top of the tower would be 96-something meters. And that's what they want. Okay. A train is traveling 23 meters per second. It brakes to a speed of 8 meters per second in a distance of 600 meters. Now, this is the first proper kinematics problem that we've had today. So let me just remind you, all we're trying to do is find the numbers. I got 1 number, 2 numbers, 3 numbers, 4 numbers. Okay? And it helps me to make a list or see a little picture. Meters per second's got to be a velocity, and that's at the beginning before it slows down. So I'm going to write V naught equals 23 meters per second, and that's this guy. Over here, it's going to slow down to, here's some more meters per second, so that's my final velocity. Distance, told me it was distance. They also say it's in meters, so it'd have to be the distance, or displacement more properly. 600 meters, and they want me to find A. Okay, now this is where it comes in, and remember that we only had 3 formulas, so all I got to do is pick the right one. And it's a pretty simple process. You've got these written down somewhere. You may bring a card to the test, a 3-inch by 5-inch card, and you may look at that card. Wouldn't do much good to have it and not be able to look at it, but I suggest that that card has V equals V naught plus AT, and X equals V naught T plus 1/2 AT squared, and V squared equals V naught squared plus 2AX. And if you had those 3 on there, plus whatever else you think you need, I think you'd be all right. What you want to do is to find the formula that has those 4 variables on it. So there's that. And I start over here and I go, yeah, I got V naught, I got V. Oh, there's no X. I'm looking for A, but I don't have T. 2 unknowns, can't use it. No good. What else you got? X, that's okay. V naught, got that. Ooh, I don't have T. And I don't have A. So I don't know T, don't know A. 2 unknowns, no good. Better be this one or we're in trouble. Let's see what we got. I got V naught, I got V. I got X. Only thing left is A. See how there's only 1 unknown there? That's our buddy. So we pull that one out over here, and I go V squared equals V naught squared plus 2AX. Just get in the habit of writing these things down. Paper's cheap. It helps you solve the problem. And it helps everybody, including me, see what you've done. And it helps you find your mistakes better, too. We're trying to solve for A, this guy. I need to clear everything off of the right-hand side. Leave the A sitting there. Here's some added stuff, so I'm going to subtract V naught squared from both sides. That will cancel on the right, and I'd be left with V squared minus V naught squared equals 2AX. Okay? Trying to leave A right there. I need to get rid of the 2. It's multiplied, so I need to divide. Always do the opposite. 2 divided by 2 would be a 1. Right? It's gone. I need to get rid of that X. So since this is multiplied, the opposite would be divide, and X divided by X would be 1. It's gone. Nothing but A left on the side. 1 times A is still A, right? So, but if I do it on one side, got to do it over here like that. And now all I got to do is put those numbers in. The V was 8 meters per second. And I really like it when my students put down the numbers here. I'm sorry, the units. Just so you can see what's happening with these things. Make sure that everything's behaving itself. Anyway, there go the numbers in this thing. I'm going to put this in the calculator. You got to be a little bit careful here with this thing. What you want to do is recognize that on top, I need that subtraction to happen before I divide by all this stuff on the bottom. And one thing that's kind of useful here is to come in, I know I've said this before, is to put some parentheses like that. Hold all of that together, make sure that happens first, and then you can even do it down here too. Make sure that you multiply 2 times 600, which would be 1200. I want to divide by 1200, right? So you could go ahead and do that in your head. You could just put it in the calculator. I'm going to put it in the calculator. Here's 8 squared minus 23 squared, and I'm going to close it up. That's my numerator. Downstairs I've got divided by 2 times 600. See how that's all inside the parentheses? You don't really have to close it here, but I'm going to. Looks just like the things there. And we get a negative 0.3875. And you say, negative? Why is that negative? And then you go, oh yeah, the train's slowing down. Okay? When you see that it is braking, it's slowing down, yikes, then you expect to see a negative acceleration. I'm hoping, because this is acceleration, that it comes out in meters per second squared. I like it when people come through here and say, well, there's meters per per second, which gets squared. So that would be a meter squared over second squared. And then downstairs I don't have anything but a meter. That's a compound fraction. Invert and multiply. And, sorry, I started to do the division. We'll do the division here. That fraction bar means to divide. And I'm going to make this look like a fraction right there. I need to invert and multiply. See how the m on the bottom cancels one of the m's on top, but not both. So I've still got a meter. I give up. I still got a meter up there. I got second squared on the bottom. So my units are right. As soon as I see the units are right, then I feel pretty good about my algebra. All right. Could have goofed it up on the calculator. Here's one alternative on your calculator. I would still use the parentheses on top. Okay, so that didn't change. But you're also okay if you go divided by 2 and also divided by 600. That'll give you exactly the same answer. So either one of those ways is okay. Either wrap it up in parentheses or divide. All right, next problem here. I'm going to throw a rock straight up into the air. It reaches a height of 17 meters before gravity stops it and it begins to fall. Let's picture this, shall we? Here is the ground. Here is the rock at the beginning. I've got some kind of initial velocity here, and that's pointed up. And that rock is going to go up, 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 up like that. It's slowing down as it goes. Why is it slowing down? Well, because gravity is pulling down. All right? And that is the acceleration due to gravity. So I'm going to call it G, call it A, whatever you want. But the value here on Earth is 9.8 meters per second squared. And just to remind me, I see this up and that down, right? Those are opposite directions. One of them's got to be a positive. For right now, let's just put an up and a down like that. They tell me at the top that it stops. So here's the rock at the top. The final velocity equals 0. After that, it's going to fall back down. But I can just kind of freeze frame it right there and think about this thing. I also know that the height was 17 meters. So I'm going to put right here x equals 17 meters. And those are the 4 variables at play in this problem. I know the final velocity, the displacement, and the acceleration, and I want v0. I need something that has this. Well, that's the same formula we just did a minute ago. V squared equals v0 squared plus 2ax. It's the same problem. Last time we were solving for the acceleration. Here we know the acceleration, and we're looking for the initial velocity. So it's very similar, and yet it's different too. Every one of these is a little bit different, and you're crafting a solution to it. You've only got 3 choices, but you're building it every time. And the more you can see it, the more real this is to you, then the better off you are. Now, to get this guy by itself, I'm going to subtract 2ax from both sides. That'll cancel that, leaving me at v squared minus 2ax equals v0 squared. And I got to get rid of the squared, so we need to take the square root of both sides. And when I have the square root of something squared, those cancel each other, and I'm just left with the v0. Okay, so that's where I want to go with this thing. We're ready to put some numbers in this. And the v squared, here's my v is 0. I'll put it in here, but you don't really have to. I've got this minus 2, subtract 2, times a. The a is 9.8 meters per second squared. And the x is 17 meters. It's actually 17 meters up. So I got to be a little bit careful here. This is where I got to think about my coordinate system. It doesn't matter which way you set it up, but you need to come over here on the side, at least in your head, and say, I recognize that I've got some up stuff. There's 2 things that are up and 1 that's down. And you need to pick a direction. Say, I'm going to call up positive. You can pick down positive. I don't care. But pick something and stick with it. Everything that points up gets a plus sign. everything that points down gets a negative sign. And we're expecting this guy to have a plus sign when we get down there. If we don't, we're kind of in trouble. Something got messed up. Okay? So that's that coordinate system. Easy to do. Just draw a little line over there. I need to put in negative 9.8 right here. The displacement was positive 17 meters. And that's purporting to be our V0 right there. So I'm going to hit square root, second squared, timed out. Isn't that cute? There we go. I've got a negative 2, I'm ignoring the 0, times negative 9.8 times 17, and that would be 18.3 right here. Once again, it would be good to look at the units and make sure that our algebra worked out. I got a meter times a meter, so that is a meter squared. And then down here I've got a second squared, like that. And those units look funny. I need to look here. Okay, I already took the square root of the number, but I haven't taken the square root of the unit. So I'm going to come in here and mark this like that. And of course the square root of meter squared would be meters, 18.3 meters. The square root of second squared would be seconds. And that's my initial velocity. If you want a rock to go 17 meters up in the air, you better throw it with at least 18.3 meters per second of velocity. All right, here's a bicycle. It's leaving a ramp, 23-degree ramp. Let's draw a picture. Here's the level ground. Here's the ramp. 23 degrees in there. My brother's a bike jumper. He was, until he broke too many bones, and then he said, I'll give that up. Let's say he's leaving here at initial velocity is 17 meters per second, and this is some important information right there, level ground. All right, that means I can come on over here and draw me some nice level ground, and my brother's going to go flying off of this ramp like so. He's going to go up, 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 and then he's going to come back down, and I get this nice, smooth, symmetric parabola right there, inverted parabola, and he's going to land on the same height that he left at. Okay? So he goes up and he comes back down. What is the range? Well, we've got three formulas that we get to use anytime it says level ground. The first one says that the time is equal to 2v0 sine theta over g. I don't want the time, so that's no good. I got one that says the range is v0 squared sine 2 theta over g. That looks pretty good. They want the range. This formula gives me the range. We're good to go. So I'm going to go ahead and put that down. Gee, I should just put the numbers in over here, shouldn't I? 17 meters per second is my my initial velocity. That has to be squared times the sine of 2 times the angle. Double angle here. So that'd be times 23. 2 times 23. I'm dividing by g, which on Earth, I'm assuming here that we're standing on Earth, not Jupiter. Would look like that. And I want to do 17 squared times the sine of 2 times 23. Need to close up sine and then divide by 9.8. And that's 21.21. He flies 21 meters. That's a terrifying prospect. That's 60, 65 feet, something like that. So good luck to him. I guess maybe that's how he broke all those bones. Here, number 6, at what 2 angles could you aim a cannon that fires a shot at 400 meters per second? There's a number. I'm really interested in the numbers. Wonder what that would be. Oh, that's my initial velocity. I'm going to hit a target 4 kilometers away. Normally, we would put that down as x for the displacement, but I can already tell that this is a level ground shot. I'm kind of assuming that it's level ground. My 2 main choices from this chapter are either level ground or a cliff problem. They didn't say anything about a cliff problem here, so I'm kind of going out on a limb, but I'm assuming that this is level ground. If it was a cliff, they'd have to tell me it was a cliff. All right, they didn't, so I'm going to go with the level ground approach here, in which case maybe instead of X we want to call this R for the range. And then I could come in here with my range formula, the one we just used. Only this time we want to find the angle, which is up inside here. So we got some unpacking to do on this thing, but we'll get there. If I come in and multiply by G, then the G on top would cancel the G on the bottom. I'll do that on both sides. I want to get rid of that V0 squared. It's on top, so I need to divide by V0 squared. The one on the bottom cancels the one on the top. If I do it on the right, I got to do it on the left. So let's let the dust clear there and see what we've got. Here's RG over V0 squared equals the sine of 2 theta. Okay? Trying to get that theta inside the parentheses, but I got to get rid of the sine first. What we do is we write it in this fashion right here. We write the arc sine of RG over V0 squared equals 2 theta. Okay, and once we have that, then all I got to do is get rid of the 2. So I'll divide by 2, or even better, let's come in here and we'll multiply both sides by 1/2. That'll make it a little prettier on the left-hand side. Okay, so there's that right there. And on the right, I just have that theta. Everything else canceled out. Okay, we're ready to put some numbers in this thing. So I got 1/2 times the arc sine. The range, was 4 kilometers. Remember how I said we don't like anything except meters? That's not in meters. So when they say that R equals 4 kilometers, the first thing, it doesn't have to be the first thing, but somewhere in there you say, I got to get this back to meters. And that would be 4,000 meters. Okay, so I'm going to use that number. Times 9.8 meters per second squared. And I'm dividing that by the initial velocity. Don't forget to square it. Initial velocity was 400 meters per second. And there's the squared on it. And let's see what that comes up to. I've got 1/2, I'm going to put 0.5, times the arc sine, second sine. Inside arc sine, I got 4,000 times 9.8 divided by 400 squared. And that would be 7.1, let's say. Okay, so that's one of my answers. I could aim this cannon up at 7.1 degrees, and I would hit the target over here 4,000 meters away. Okay, so good for us. But the problem actually said there's 2 angles. There's a second angle that works, and finding the second one's, once you got the first one, is super easy. The other one comes about whenever you shoot this thing way high up in the air, and it goes up, 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 and comes back down like that. So we're interested in this angle right there. I'm going to call it theta 2, and this will be theta down here, the one we found. To get theta 2, you just take 90 minus the first one. So here that would be 90 degrees minus 7.1 degrees, and we're looking at 82.9 degrees. So either one of those would work. You could think about a cannon, you could think about a mortar. Either one would drop it in right there. All right. Number 7, I got a car driving off a cliff. Whoa, see that word right there? This must be a cliff problem, right? So we get our little cliff ready here. I don't know why you want to drive a car off a cliff, but my son and I were driving through the Southwest years ago, and there was a cliff, and there were not 1, not 2, but 3 cars at the bottom of that cliff. I don't understand, but that's the way it went. A car drives off the top of a 27-meter high cliff. So I'm going to come in here and say the height of that cliff. Let's say y equals 27 meters. To be explicit here, notice that the car starts at the top and falls down to the bottom. So I'm going to put 27 meters down right there. The question says, how far from the base does it hit? They want to know this direction. How far to the right does it go? So I'll put x equals question mark right there. I do have this number. It says how fast the car is going. And that's 15 meters per second. So I'm going to put V naught, the initial velocity, 15 meters per second. The trick to doing all of these cliff problems is to break everything out in x and y direction. You got to keep these things separate. So, really, normally we have V naught and V and A and X and T, a list of variables like that. Well, here you need to do that twice. V naught, V, A, I'm going to put a Y instead of an X, and a T right there. And it would be good to say this is V naught X, VX, AX. That's already got an X. T doesn't have a direction associated with it. This would be V naught Y, V sub Y, A sub Y, Y. T doesn't need one, right? So we're not saying that the initial velocity times X. That's another little subscript there to remind us that I'm only thinking about how fast this car is moving in the X direction, left and right. And over here, how fast is that car moving up and down in the Y direction? Well, when they tell you it's horizontal, this is a 0, and this is all of it. So I'm going to put the 15 meters per second right there. Final velocity, they don't tell me anything about that. And honestly, I don't need that, so I'm going to mark that one out. A sub x, A sub y, that's the acceleration. The car is going to accelerate downwards because of gravity. So that's my A sub y. But guess what? Gravity does not pull sideways, and the car's wheels aren't making it go any faster to the left or right. There's nothing slowing it down. Once it goes off the cliff, it's going to keep moving that speed until it falls and hits the ground and comes to a stop. This is what we're looking for. The height here was 27 meters. That was a down. Actually, this gravity is a down also, isn't it? Let's put that in. And I don't know the time. I don't know the time. These will be the same time, and I don't know the distance. If you notice over here, I got 1, 2, 3 numbers that I do know, and one that I don't. Over here, I've only got 2 numbers that I know, and 2 that I don't. I can't solve this guy yet. So I need to do this first, get T, and then port it over there, recycle it over there. So I'm going to use the displacement formula in the y direction, which would look like this. And by all means, whenever you see that one of the numbers is 0, then use that information. 0 times t would be 0. That cancels out. That makes the problem a whole lot easier. Otherwise, you'd have a quadratic right here. We were trying to solve for t. So we get busy, do some algebra here. In this case, I need to multiply by 2 to cancel the 1/2. I need to divide by a sub y to cancel the a sub y, top and bottom there. If I do it on the right, I got to do it on the left. So now I'm right there. This is gone. That's gone, that's gone. The only thing left is t squared, and I don't want t squared, so I need to take the square root, nothing over here except the t squared, but I'm going to put it there, and then the square root and the squared cancel each other, and I have t by itself finally. If I do the square root on the right, got to do it on the left, like that. So the numbers I want to put in here would be 2 times the height, and this is a 27 meters down. And here's the point where I need to decide, is up positive or down positive. We'll go ahead and put the numbers in here, and we'll argue about the signs like this. Choice A. This is what most people do. They're more comfortable calling up positive. If up is positive, This is down, so he gets a negative. This one is down, so he gets a negative. And I'd have to come in here and put negative and negative, and you can see that that negative and that negative are going to cancel. And I'm okay. It's not the square root of a negative number anymore, so we're good. Plan B, this is totally your choice here, is to say, well, shoot, I'm going to call down positive. This guy's down and this guy's down. I don't have anything pointing up. It would just be simpler to not deal with those negative signs at all. And I'm going to call down positive. So now this guy would be positive and this would be positive. And that would mean I'd put a plus sign and a plus sign, and it'd still all be positive, and I'd still get exactly the same answer. And that answer looks like this. The square root of 2 times negative 27 divided by negative 9.8. Okay, and that's 2.35 seconds. Now, I guess it wouldn't hurt to stop right there and say, if you didn't get your signs right, let's say that for some reason we called the bottom one positive and the top one negative. They both point down. They both got to be the same sign. But if you goof this thing up, just let me show you what would happen. Here is that. I'm going to take out this negative right there. See how it blows up your calculator? Calculator says I can't take the square root of a negative number. Okay? So if you see that happen, just check your coordinate system. Make sure that everything's good. All right? And let's pull that back up just so I can... yeah. That's interesting. One more. That's funny. Okay. Whatever. I'll do it again. I got the number there. Okay? That's not what the question was asking. They wanted the x distance. So we got a little bit more to go on this one. Right here, I'd use the same formula. X equals v naught xt plus 1/2 a sub xt squared. We did it once in the y direction. Typically, you do it first in the y direction to get time, and then you do it in the x direction, and we're trying to get x. Okay? Well, it's already solved for x, so we don't have to do any algebra. It gets even better because a sub x is equal to 0, and 1/2 times 0 times t squared is 0, so that's gone. All I have to do is multiply the initial velocity in the x direction, right there, 15 meters per second, times the time, t, which we just found to be 2.35 seconds. And we're up around, I don't know, 37 or something like that. Let's see what it is. 15 times 2.35 is 35.25. Okay. The second here cancels the second there, nothing but meters left, which is good because we were looking for a distance. That was number 7. Number 8, I've got a car moving 2 meters per second when it accelerates at 3.2 meters per second squared. How fast is it going 10 seconds later? All of these kinematics problems, this one is not a Cliff problem. This is just a regular old kinematics. But we're looking for the numbers, and we're trying to find a formula that ties those 4 numbers together. In this case, I got a v naught, I got an a, I got a t, and we're looking for final velocity. The formula that we need looks like this. Okay, and I think we can just jam everything in. We're looking for v, right, which is this guy, and I've got v naught, a, and t. You see how the game's played? It's not that bad. You can do this. 2 meters per second plus 3.2 meters per second squared times 10 seconds. That'd be 32, and 2 is 34 meters per second. You could look at the units there. This should have had a second. Second cancels one of those, leaving the meters per second. I add that in meters per second, I get meters per second, which is right where I want to be. Okay, how much time would it take a snail? Right, so there's the first number right there, time, t, and 2 meters per second is the initial velocity. It's going to come to a stop That's one of the numbers there. The final velocity is 0, and I've got a deceleration. It told me so. The unit also told me so. Notice it's negative. Why is it negative? Oh yeah, because the snail is slowing down, coming to a stop. Okay? Now you probably want to know if I can draw a snail or not, and the answer is probably not. But I like a challenge, so I'm going to try here. And I guess that wasn't half bad. You could come in here and label all your numbers if that helps, by all means. Yeah, even better there, huh? You know, somehow get this in your head and see what's going on. That's supposed to be an A equals negative 0.42 meter per second squared. Okay, need a formula, and this looks like the same one we just used again. V equals V naught plus AT. Every time I do one of these, I'm thinking back to that list that we have. I'm just checking off the possibilities, and it's really process of elimination. You learn the principle and you apply it. I've always thought it was kind of like having a toolbox, you know, and some days you need a screwdriver and some days you need the pliers, and once in a while you need a hammer, right? So when I go through here and say I got to solve this problem, and sure enough I have V naught and I want to know the time, I'm trying to stop, I know the acceleration, I see 1, 2, 3 that I know and 1 that I don't. That's what I'm going to pick up. I'm going to grab the screwdriver, right, and make this happen. I'm trying to solve for time, so I got to move some stuff around here. That's going to involve subtracting V naught from both sides and dividing by A. But once I've got it there, I put my numbers in and see what happens. This would be 0 meters per second minus 2 meters per second divided by negative 0.42 meter per second squared, and you get a number there, whatever it is. I get 2 divided by, I can't let the negative numbers cancel out. I got a little sloppy with that, but 4.76 seconds would be the thing there. If you put them in, you get the same thing. Good? Okay. Number 10, I got a skateboard. It's going to roll down a hill. So let's draw something here. There's a skateboard at the bottom. Here's the skateboard at the top. And it starts from rest, so V naught equals 0. It's going to roll down the hill, covers a distance, a displacement of 300 meters in a time 15 seconds. They want the acceleration right there. So I'm looking for a formula that's got those. X V naught AT, that looks familiar. X V naught A and T would be this guy, and A is what I want. Here's another one where they say V naught equals 0, so by all means come in here and say 0 times T is 0. When I add 0 it doesn't do anything. I can multiply both sides by 2 and divide both sides by T squared. That'll leave me A all by itself. And 600 divided by 225 is going to be about 1.7 or something like that. 2 times 300 divided by 15 squared. Oh, I messed up. 2.7. 2.7. I got a meter on top. I got a second which gets squared on the bottom. And sure enough, that's acceleration. Things speeding up, I got a positive acceleration. Checks out. Here, this problem does not belong in this chapter, actually. This is much later. Well, actually, you can. No, you can't do this. All right. Next, jogger is moving at 2 meters per second when he realized he's being chased. He accelerates. How long does it take him? Now, that looks like a kinematics problem. I'm going to write down the numbers here. V naught equals 2. A equals 1 meter per second squared. Find the time to reach a velocity of 5 meters per second. Man, that's the easiest one of all. All right, V equals V naught plus AT, and I'm looking for T, so I'd have V minus V naught over A equals T. See what I did there? I subtracted V naught from both sides. Had to divide by A, got to divide by A. End up right here. Put the numbers in. You can do that one. Just don't forget to put your parentheses around the numerator here so that you do the subtraction before the division. I think this is the last one. Here we're throwing a rock downward. So I'm going to put a rock up here at the top. The initial velocity is down. Trick to getting this right would be to get all your signs right. How far does it fall? X equals question mark in 12 seconds. Now, that's only 3 numbers, and you know you got to have 4. But presumably we're on Earth here, so I'm going to put 9.8 meters per second squared here. The acceleration due to gravity on Earth. That's also down. Okay. A quick thought about your coordinate system convinces you that since this one is down, and this one is down, and the distance is down, everything is down, that one option would be to call down positive, and then all these numbers would have positive signs in front of them. Plan B is to say, no, I want to call up positive. And in that case, this down got to get a negative sign. He needs a negative sign, and we're expecting the answer to come up negative. All right, it's up to you. I'm going to go with the red stuff here. I don't really like negative signs, so we can just bypass all of that. And, of course, what are we doing here? Looks like the displacement formula, right? X, V naught, A, and T. So I'm going to write the X equals V naught T plus 1/2 AT squared. Okay? I got a bad feeling about this, but actually it's going to work out fine. Here's X. That's what I'm looking for, and I've got all of these. I thought we were looking for time there for a second. Then go back and read the problem again. In that case, you'd have a quadratic here, and you'd have to do a little bit more chewing. But as it is, we've just got the numbers, so we'll go 4 meters per second, 12 seconds, plus 1/2 times 9.8 meters per second squared, times 12 seconds. Don't forget to square this guy gets left off so often. Makes him feel bad. Makes me feel bad too, so don't do that. 4 times 12 plus 0.5 times 9.8 times 12 squared. All right, 754 meters will be good enough. Okay. Ha! I lied. There is one more. All right. A rock is thrown upwards at 4 meters per second. 4 meters per second up. That would be the initial velocity. How fast is it moving? What's the final velocity? 12 seconds later, like that. Once again, this problem has gravity. They didn't mention it, but don't forget that it's in there. A, check. All right. So V naught, V, A, and T, that's formula number 1 again. We're looking for this guy. So it's really a matter of getting your signs right, your coordinate system right, getting everything in the right place. This was up. Acceleration is down. See how I've got some up and some down? Something's got to be negative. All right? So I'm picturing a rock that's here. It gets thrown up into the air. It's slowing down, and then eventually it's going to stop and fall back to Earth. Okay? Now, I don't know where 12 seconds, maybe it's still going up after 12 seconds. Maybe it's reached the top and it's coming back down. We just don't know. But the formula does. So if you'll just put the numbers in, see what it says. V naught was 4. Let's call up positive, shall we? That would make this guy that's pointing up positive, and it would make the acceleration, which is down, negative. Okay? If I do it that way, I got a 4 meters per second plus negative 9.8 meters per second squared times the time is 12 seconds. And here I've got 4 plus negative 9.8 times 12 is negative 113.6. Okay. Evidently, we were standing at the edge of a cliff, threw that rock up. It came to a stop up here. We'll call this V2 or something. It's not the final velocity because it's still falling. But that thing went all the way up, turned around, and now it's going down. The final velocity down here is down. How do I know? Because it's got a negative sign. It told me so. Okay. So those are some kinematics problems. I would be happy to work some more of those with you. If you'll just call me or text me or email me, and let me know that you want to get on Zoom or whatever we can do. Just let me know. It'll be all right. All right. Thank you for your time, and I wish you a good day. Thank you.